Thank you, and good morning, everybody. Thank you for coming over and spending your time with me to go over another technology which uses the process technology that Dongbu has. We are very excited about working with Dongbu, one of our better technology partners, and we've been working with Dongbu for a number of years. Again, I'd like to talk about digital power today, which uses the technologies that Dongbu has to offer. Many products we have in development that use Dongbu, and this is just another example. Okay, so why do we care about digital power? First of all, for many years, system designers have realized that one of the most exciting and bottlenecks of the system performance is actually power management. And of course, interfaces that Jeff talked about previously. So power management has been one of the main bottlenecks for many system designers, such as mobile devices or servers. And I'll get into that as to why. But one of the ways that the industry and academia, universities have responded is by implementing digital power. So digital power promises us better power efficiency. It promises us lower cost, flexibility in the system design, and this is what I'll be talking about today. So what I hope you walk away from this talk is a basic understanding of what digital power is, what markets it serves, and where it's going to be headed in the future. So before we get deep into what digital power is, I'd like to point out that there has been much debate about the actual definition of digital power. So I will talk about that first. So a typical power supply or a DC to DC converter can have a control loop that is analog or digital. What I mean by that is that the pulse width modulators can be either an analog pulse width modulator or a digital pulse width modulator. So when we implement the feedback loop in the digital domain, we use a discrete time domain approach. That is basically a digital power supply, and that is one form of digital power. Another case is when we actually control and monitor the power supply through a communication bus. That's also referred to as digital power. So these two definitions somewhat seem to be very different, but people kind of refer to digital power interchangeably, and it's important to keep them separated because they're really not the same and they're very different. So at the heart of it is that basically we have a DC to DC converter, an input voltage, an output voltage, where the core of this DC to DC converter could be either analog or digital. In this case, we're talking about the digital core, and a communication bus that communicates to this power supply or DC to DC converter. So why is it important? We believe that by 2015, about 10% of all onboard power supplies or DC to DC converters are going to be implemented in the digital domain. Now, this is very important because it's actually a fairly significant market opportunity for many semiconductor suppliers. And also it's important for our foundry partners. Because what that means is that if it actually, this market transitions toward digital power, the requirements for companies like Dongbu and our technology partners will change. And I will get into that in a few slides of what I mean by the requirements changing. What will require to implement these kind of products are very different from the classical analog power management kind of products. So yeah, we believe this is going to be a $900 million market opportunity for us. This is only the power management controller section. Of course, there is much more money to be made even outside the controller, because there is also smart power devices, power FETs, and so on, magnetics, capacitors, inductors, all sorts of other things. But the market opportunity for the semiconductor PWM block is $900 million in 2015, which is 10% of the power management market. And of course, it will be growing even beyond that as the years go by. So it's a significant market opportunity for many semiconductor manufacturers and power management manufacturers. So let's take a look at a simplified block diagram of a digital power system. So in a typical system, there is not one voltage rail that people are controlling, there is multiple voltage rails. In this case, I'm showing 3 voltage rails, but I must tell you that a typical server, for example, on a server board, there is somewhere between 10 to 20 different power rails that a board may have. In a mobile system, there may be, in a cellular phone, there may be, again, 4 or 5 different voltage rails and many different subsystems for the different power management blocks, for the different blocks within a mobile phone. In any case, there is multiple DC to DC converters controlling multiple voltage rails. All of these voltage rails are under control and monitoring of a host communication bus. And of course, the main job of this DC-DC converters is to take the input power and control and output voltage. So this is a basic block diagram that you will see in either a mobile device or a server or any kind of a board, a power management board. Now, what do we use the digital power for? There's multiple uses for it. First is monitoring. Monitoring things like output voltage, output current, different temperatures around the board, and basically fault monitoring, monitoring the different faults within a system. So we need a communication bus to monitor all these faults. And also the second is programming things like output voltage, current limit values, or things like behavior of the system in response to various faults. So we actually would like to control and program the power rails when certain events happen. So again, we need a communication bus in order to do that. So event-driven sequencing of various power rails is very important. And of course, I also talked about digital control of the main power supply, of the core of the feedback loop. Now, I will get back to that, why that's important, because it's important for our technology partners to realize that if that happens, and when that happens, I think it's not a question of if, but when, most analog blocks within a power management chips will actually disappear. So when these analog blocks disappear, of course, the technology requirements will change. So the main applications of digital power are portable devices, and we saw that, for example, back in 1995, Intel pushed a standard called SMBus for communication to power management devices. So notebook computers are actually early adopters of digital power. At the time, there was not, back in 1995, there was not such a word, digital power, but actually Intel did push the concept of SMBus back in 1995. We just didn't call it digital power. Back in 2007, there was another specification that came out called PMBus. That specification was written mainly for point-of-load DC to DC converters within server power supplies. And we've seen the applications of digital power within server rails. Now, why do we care about servers? It's because servers have many, many different power rails within them. Many servers are mission-critical servers, where they are processing critical applications such as e-commerce or banking. So these servers need to be fault tolerant. That means we need to read all the voltages, all the currents, all the temperatures, and various system parameters in real time to make sure we have backup power all the time. So the only way that we could actually solve this problem is by digital power. And of course, another large and emerging market is LED lighting. Now, why do I talk about LED lighting? Why does digital power care about LED lighting? In a typical LED application, there is many different types of LEDs that people put in their households or different fixtures. These different LEDs, to make the matters even more complicated, they actually have different types of dimmers. And dimmers vary by type and by many different types. So the only way that we could actually have our LED driver adapt itself to the actual installation of the LED type and dimmer is through the use of some digital technologies. So we have seen many products from some suppliers where they use a digital power chip to adapt the control of the LED with the different dimmers that are installed within a installation. So this is one way that people have solved the problem of adjusting and adapting the LED installations and the driver to the dimmer types that are already installed in the household appliances. So you can see that digital power has a lot of different applications, and this is only a very few types that I've listed here: mobile devices, servers, LED lighting. But the number of applications of digital power are actually increasing every day, and every day somebody comes up with another application that can use digital power technologies. So what's important is that for a number of years, I would say for the last 10, 15 years, there was a lot of debate about whether or not digital power will actually find an application that would be the killer application that people cannot live without. And people debated whether the digital power was here to stay or whether it was a fad and was going to go away. But as we have seen, we're finding applications, more and more applications every day, and more people are solving. The only way they can solve different cases of problems is with the use of digital power. So for mobile devices, one of the most important critical factors is efficiency of the power conversion and power management. For example, the battery life, the charging time, and how long the battery lasts in your system really depends on the power management subsystem and how each subsystem is controlled. For example, there are multiple different subsystems such as battery charging, the display, sometimes a keyboard. All of these could be connected through a communication bus and could be actually powered down when they're not in use. So we need a digital power communication bus in order to actually communicate to each one of these subsystems. This allows us to optimize battery life of a mobile device. So all of the power management subsystems need to communicate with each other and to a system host. In a data center, I already talked about this case, but what's even more important about fault-tolerant servers is the fact that in a typical data center, the cost of a data center is dominated by the operating costs of a data center, costs associated with cooling and air conditioning of a data center. So the only way, one of the ways that people have been able to come up with improving the power efficiency of the servers is through the use of digital power, and I will show you how we can do that in a minute. So efficiency of the servers is going up because we can actually monitor different rails and we can shut them down when they're not in use. When a power rail is not needed, we can shut it down. We can put it in low standby modes, and so heating costs are reduced and operating expenses are reduced. So data center requirements have put basically digital power at the forefront of power management. So as I pointed out, there is a standard called PM bus that the industry came up with back in 2007 that is now the de facto standard for power management of point-of-load converters within server applications. Okay, so digital power is really used because of two reasons. The first is cost. So enhancing cost relates back to enhancing performance. When we can enhance the performance of a power management of the power rail, for example, line and load transient responses, if we can reduce those, we can reduce the number of capacitors that are used within a system. That reduces our cost. It also reduces the footprint area, and it reduces the power dissipation of those components. Digital power also allows us to have an integration path toward the elimination of all the analog components. So not only the communication bus is in the digital form, but also the analog controller does not exist anymore. Almost all of the components within the system are implemented in the digital domain. But another thing that digital power brings us is flexibility. Things like system parameters can now be adapted after deployment. For example, we can actually design the hardware of a system, the hardware of a server, for example, and then program after the deployment each power rail. And all the fault monitoring and events that need to happen during those faults, in response to those faults, can be programmed after deployment of the server. So this reduces our design time, the time that the system designers spend in designing a server. So digital power promises to bring to us not only reduced cost, but also flexibility of the system. So I talked about the communication requirements. So obviously we need to communicate to the various DC-to-DC power rails and power supplies. So there was two standards that the industry has come up with. The first is SM-Bus. This came out back in 1995 by Intel, and Intel required the various power rails to communicate to their system host controllers through a SM-Bus interface. SM-Bus is a purely physical layer interface. It does not have any command language. So there is still significant interoperability issues with SM-Bus. So back in 2007, the industry came up with another standard called PM-Bus. PM-Bus now uses the physical layer interface of the SM-Bus. And by the way, both of these are very similar to I2C. But what PM-Bus brought into the standard is a command language. So designers can actually design the hardware, and the software designers can then, at the end of their deployment of the system, then actually write the program to program all the power rails, various fault conditions, and so on. So interoperability came in play. So, it's also important to note that both of these are actually serial buses. Serial buses are slow, relatively slow. So it's important to keep in mind that now we have two main serial buses, SM-Bus and PM-Bus, but they are still serial buses and they are still very slow. So this is important for where we are headed, and I will get to that in a minute, because I think that the serial buses and slow responses need to be overcome. So let's talk about digital feedback control for a minute. What is it that digital feedback control brings us? In this case, we have a discrete time domain algorithm, a DSP engine, essentially which is at the core of the feedback loop, which controls the output voltages. So what this allows us to do is now, again, elimination of the analog components of the power supply. That means all the PWM circuits that people are designing can migrate into a fine geometry CMOS technology. So it is not here yet. People have not done it, but we see signs that the industry is moving to more and more toward implementing PWM blocks and DC-to-DC converter blocks on board the microprocessors and SoCs that people are developing. So let's take a look at a block diagram of such a system. In this case, we have an input voltage which goes through a power stage, which powers the load. Now the output rail goes into an analog to digital component, which then goes into a PID control loop, which controls a digital pulse width modulator, which then controls the power stage, and that's how the feedback is closed around the loop. So you can see almost the only components that are you could say it's in the analog domain is probably the ADC, analog to digital converter. The rest of these blocks are mainly in the digital domain. And of course there is some system monitoring which communicate to this whole thing through the communication bus. Now when we actually can control now this PID control loop, and we can control the various coefficients of the PID control now in real time, that brings us some interesting results, because now we can actually adapt the system to the events that are happening in the system in real time. And we can actually control the system in real time. In other words, the PID coefficient loops and the feedback loops can be actually adapted in real time in response to various faults and errors and transient response that are happening within a system in real time. So, of course, this is a very simplified block diagram. Now let's take a look at a little bit more detail, like more of a real chip that people have designed. This is a product that actually my company, Micrel, has. I just wanted to show you an example of the complexity of this kind of product. So here's a typical chip architecture. One of the first blocks is the current sensing. Now the current sensing, what can we do? Obviously any power supply needs to monitor the current. But what we can do with digital power technology is now to calibrate the current that is being measured. We can also calibrate the temperature and the variation. We can take out the temperature variation of the current sensing signals with the digital power technology. So if we can sense the temperature, we can then calibrate it out. The next is digital control loop. So as I pointed out, the control loop can be implemented in the digital domain, and now we can actually adapt the control loop, the feedback control loop, the coefficients of it, for optimum line and load transient response. And I will show you that in a second, that this product is actually capable of nonlinear gain control. In other words, we can control the gain of the loop, the feedback loop, when a load error happens. And that minimizes the load transient response. Next is protection. So all the things like input voltage, output voltage, over voltage, temperature can be all monitored, and we can control and program how the chip responds to these various fault conditions. And of course, last but not least is the communication bus. So the chip has a communication block, which in this case is a PM bus architecture. So the chip has a specific command language that you could talk to it. This is an industry standard command language, and you could program all these various things, such as over temperature shutdowns, over current conditions, all output voltages through the specific PM bus command language. Now, here is the performance, a load transient response of the chip, which is compared to an analog controller. We just basically programmed the chip to have the same transient response as a typical analog controller. And you can see that the transient responses are almost identical. Now, but what we can do with the digital control loop is to actually program it for nonlinear gain control. In other words, we can control the loop gain during the transient response, and we can program it to say if the load transient is not good or beyond a certain level, then change the gain of the system, which in that case, you can see the digital control loop kicks in and reduces the transient response. Now, what does this mean is that we now can eliminate the output capacitors that are associated with the power supply. So we can reduce the number of output capacitors. By the way, in a typical power supply, capacitors are the dominant cost associated with the DC to DC converter. So when the transient response cuts in by half, the cost of the capacitors associated with the output voltage go down by half. So much faster settling time due to with the use of nonlinear gain control. Now, where are we headed with this technology? Now, I pointed out that with the digital power technology, the industry is going toward integration of the PWM blocks into the SoCs and microprocessors. And with the use of digital power technologies, we believe that in the next few years we'll see more integration of the control loops of the power supplies actually being implemented and the analog blocks being eliminated. So where are we now is that we have a microprocessor. For example, this could be an Intel microprocessor, which has some knowledge of the internal temperature of the microprocessor, and it also has some knowledge of the load that it's trying to that it needs. It knows what load it is imposing on the power bus. This is output voltage. Now this processor sends those information over a serial communication bus to the DC to DC converter, which then controls the power bus and controls the output voltage to the processor. This is where we are today. And there is a serial communication bus, in this case a PM bus, between the processor and the DC to DC converter. This is where we are today. And in fact, as I pointed out, Intel, for example, back in 1995 mandated the SM bus communication, and one of the things that they monitor is the temperature. In fact, Intel was one of the early adopters of placing a temperature sensor onto their microprocessor. So here's a possibility. In this case, the processor has a digital PWM block actually integrated onto the processor, and in this case, the serial bus is now eliminated. So what can we do with that, and why should we do that? It has to do with onboard and real-time monitoring of fault conditions, onboard and real-time monitoring of the transients, and no delay between the microprocessor and the control of the power supply. If I have no delay between the voltage requirements, then I can actually minimize the transient responses even more. And this is the promise that digital power brings to the SoCs and microprocessors, is that if we can eliminate the serial bus and the delay associated with it, we can now have better transient response. So I'd like to talk about, assuming that is the path that companies are taking, and we do see signs that many companies are actually thinking. I've had discussions with many different chief technology officers of many companies that are producing things like FPGAs or microprocessors, and they're all thinking in these terms. What does this mean for our foundry partners, and where are we headed with the technology? What does it mean for them? So as you know, the power stage is the main dominant factor of setting the efficiency of the power supply. And efficiency is still important. The efficiency of the DC to DC converter is very important because, again, heat dissipation needs to be minimized. So what we need to do is now focus on developing power stages that are even more power efficient. And as the processor voltages are coming down, what we see is that not only the transistors need to have better on resistance and better gate charge, they also interconnect becomes a very important portion of the dissipation. So a typical microprocessor these days may impose a load of 60 to 120 amps on a rail. 60 to 120 amps is not a trivial current to deal with. So what we need to do now is actually focus on not just the transistors, but also the interconnect technology associated with that. So we talked about integration of the control loop on the CMOS chips, and I think that is a reality, and it will happen. But what that means is also the power stage, because of the technologies that are really not compatible with fine geometry CMOS, may have to stay off board. At least for the foreseeable future, may have to stay off board. So at least the way I see it is that the power stage technologies may have to get more and more optimum, but stay off board. Interconnect technologies become more and more critical, and will stay off board, so that we can keep the cost of the system still reasonable. Because I think it's still pretty unreasonable to expect that we can have a very superior on resistance and gate charge and interconnect technology on a fine geometry CMOS. So this is where we think the industry is headed, and but in short, I believe that digital power is here to stay. Its form is going to evolve, and we need our foundry partners to keep working on not just better on resistance and gate charge, but also better interconnect technologies. So thank you, and I will take some questions, I hope. Thanks.